A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. So Daniel sent us this one, and it's a meaty one. He's asking, how do you actually measure whether your AI agent is good? His point is that the LLM world has its benchmarks. MMLU, WebArena, Human Evil, but agents are fundamentally different. You're not evaluating a single answer. You're evaluating dozens or hundreds of actions, tool calls, state management, and a final outcome that might be right even if the path was broken, or wrong even if the path looked reasonable. He wants a practical guide covering the major benchmarks: SWE-bench, AgentBench, GAIA TaskBench, WebArena, plus the gotchas and the emerging evaluation approaches like LLM as judge and custom harnesses. Basically, how do I know if version 2 of my agent is actually better than version 1?
This is such an important question right now because the field has built a lot of impressive-looking infrastructure around agent evaluation. And if you don't know the gotchas, you can make genuinely bad decisions based on the numbers. The evaluation landscape has matured enormously, but the ways to be fooled by it have multiplied just as fast.
And by the way, today's script is powered by Claude Sonnet 4.6. Just noting that for the record.
Right, the friendly AI down the road. Okay, so let's start with the foundational question: why is agent evaluation fundamentally harder than LLM evaluation?
I mean, the obvious answer is that with a single-turn LLM, you have one output. You can check it. With an agent, you have a trajectory, potentially hundreds of tool calls, branching decisions, state accumulation. The final answer might be correct because the agent got lucky, or wrong because one tool call in step 14 returned a bad result.
And the scoring problem compounds that. With something like MMLU, you have multiple choice. Ground truth is trivially defined. With an agent doing a software engineering task, you need to decide, do you score the final patch? Do you score the trajectory? Do you use the existing test suite? Each of those choices encodes different assumptions about what good means.
So let's get into the benchmarks. Where does the field actually start?
SWE-bench is the canonical starting point. Princeton and CMU released it in 2023. The setup is elegant. Take real GitHub issues from popular open source Python repositories, Django, Flask, scikit-learn, SymPy, and ask an agent to fix them. The agent navigates a real codebase, writes a patch, and the benchmark runs the existing test suite. Pass the tests, you get credit. Fail, you don't. No partial credit, no LLM judge. It's execution-based.
Which sounds clean until you realize the test suite itself might be wrong.
That's the first big gotcha, and it's not a minor one. The SWE-bench verified contamination story is probably the most important development in agent evaluation in the past year. Verified was the gold standard through most of 2025. OpenAI ran an audit and found that every frontier model they tested, GPT 5.2, Claude Opus 4.5, Gemini 3 Flash, could reproduce verbatim gold patches for certain tasks. The models had seen the test data during training. On top of that, 59% of the hardest unsolved problems had flawed test cases.
So the test suite was grading on a curve, and the curve was wrong.
The numbers make it undeniable. Claude Opus 4.5 scores 80.9% on verified. On SWE-bench Pro, which is the replacement benchmark, that same model scores 45.9%. Same model, 35 points of difference. That gap is almost entirely contamination and task difficulty.
35 points. That's not noise. That's the benchmark lying to you.
OpenAI has stopped reporting verified scores entirely and now recommends SWE-bench Pro. Pro was built by Scale AI's Seal Lab, 1,865 tasks across 41 repositories in Python, Go, TypeScript, and JavaScript. The average task requires 107 lines of changes across 4.1 files. Compare that to the median of 4 lines in Verified. It uses GPL licensed and proprietary code bases specifically to resist contamination.
And the Pro leaderboard looks very different from the verified leaderboard.
Completely different. On Pro with standardized scaffolding, Claude Opus 4.5 is at 45.9%, Claude Sonnet 4.6, Gemini 3.6, Gemini 3 Pro at 43.3, GPT-5 High at 41.8. The models are much more tightly clustered, which is what you'd expect from a harder, cleaner benchmark.
There's also SWE-bench Live, which Microsoft keeps refreshing monthly.
Right, that's the contamination prevention approach through continuous updates. Live has 1,565 tasks as of mid-2025, supports 8 languages including Rust and C#, and the top score is SWE Agent with Claude 3.7 Sonnet at 17.67%. Dramatically lower than verified. That's what genuine difficulty on unseen code looks like.
Okay, one thing I want to flag before we move on. The scaffolding gap. Because this is something that I think trips people up constantly.
This is critical. On SWE-bench Pro, the same Opus 4.5 model scores 45.9% on Seal's standardized scaffold, 50.2% with cursor scaffolding, 51.8% with Augment Code's Augie, and 55.4% with Claude Code. That's a 10-point swing from the same base model depending entirely on how the agent manages context and tool calls.
Which means when you see leaderboard comparisons between different agent systems, you're often comparing scaffolds, not models.
That's exactly the trap. Seal's value is precisely that it holds the scaffold constant. When someone self-reports a score with their custom harness, you have no idea how much of that score is the model and how much is their engineering.
Let's talk about GAIA, because the original result there was genuinely shocking.
GAIA came out of Meta and Hugging Face in 2023, and the setup was deliberately designed to expose the gap between what frontier models score on academic benchmarks and what they can actually do. 466 questions that are conceptually simple for humans. Things that require multi-step reasoning, web browsing, code execution, handling PDFs and images, but that AI systems consistently fail at. The original result, GPT-4 with plugins, scored 15%. Human participants scored 92%.
Which was the benchmark that made everyone realize that passing the bar exam doesn't mean you can do what an office worker does.
And the leaderboard situation on GAIA is a perfect illustration of the self-reporting problem. On the Hugging Face leaderboard, which accepts self-reported results, the top score is 92.36% from an Alibaba cloud agent. On Princeton's HAL leaderboard, which uses standardized scaffolding and independent verification, the top score is 74.55%, the HAL generalist agent with Claude Sonnet 4.5.
18 points of difference between self-reported and verified. That's not a rounding error.
And HAL does something that no other major benchmark does. It tracks cost. Claude Opus 4.1 High costs $562 to run on GAIA. O4 Mini Low costs $73 for similar accuracy. Gemini 2.0 Flash costs $7.80 for 32.73% accuracy. HAL plots a Pareto frontier, accuracy versus cost, and labels which models are actually Pareto optimal. Claude Opus 41 High is not Pareto optimal because Claude Sonnet 45 achieves higher accuracy at a third of the cost.
This is the thing that drives me slightly crazy about most benchmark discussions. Accuracy in isolation is almost meaningless for production deployment.
Because the question isn't what's the most accurate agent. It's what's the most accurate agent I can afford to run at the scale I need. And those are very different questions. An agent that costs $500 per run on a research benchmark might be technically impressive and practically useless.
Latency too. No major public benchmark reports wall clock time.
Right. HAL uses completion tokens as a proxy, which is imperfect, but some O3-based agents on GAIA take 45 minutes to complete a task. That might be technically correct and operationally a non-starter, The benchmark doesn't tell you that.
Okay, let's move through some of the other major benchmarks quickly. AgentBench.
AgentBench from Tsinghua is interesting because it's explicitly multi-domain. 8 distinct environments: Bash commands, SQL queries, knowledge graph navigation, a digital card game, lateral thinking puzzles, household simulation, web shopping, and web browsing. The original 2023 results showed GPT-4 at a score of 4.27, dramatically ahead of everything else, Claude 2 at 3.51, and then open source models mostly below 1.0.
The gap between commercial and open source was enormous at that point.
The main failure modes they identified were poor long-term planning and inability to maintain context across many turns. What's useful about AgentBench is the cross-domain insight. An agent that excels in web tasks often fails badly in code and database tasks. Never characterize an agent's overall capability from a single domain benchmark.
TaskBench is one I want to make sure we cover because it's testing something different from the others. It's not, did you complete the task, but did you decompose and sequence the tools correctly?
TaskBench from Microsoft Research Asia evaluates the full pipeline of task automation, decomposition, tool selection, and parameter prediction. It's built around what they call a tool graph, a formal representation of tools and their dependencies. The key insight is that they generated the dataset using a back-instruct method, start from a subgraph of the tool graph, then use GPT-4 to generate a natural language instruction that would require exactly those tools in that dependency order. So you're testing whether models can invert that process.
And the finding about edge prediction versus node prediction is striking.
Edge prediction. Understanding tool dependencies, the sequencing is consistently about 20% harder than node prediction, which is just identifying the right tools. GPT-4 scored 81.54 on node F1 but 54.7 on edge F1. Models that can select the right tools often can't correctly sequence them. And code pre-training improves tool prediction by 4.45% and parameter prediction by 12.76%, which tells you something about why coding-focused models tend to do better on agentic tasks generally.
Let's talk about WebArena and OS World, because those are the benchmarks that feel most directly tied to the stuff people are actually trying to build.
WebArena from CMU gives you a self-hosted web environment, replicas of an e-commerce site, a Reddit-like forum, a GitLab-like coding platform, and a Wikipedia-like content management system. 804 tasks, binary passed, sale, evaluated programmatically without an LLM judge. The human baseline is 78%. GPT-4's baseline score in 2023 was 14.9%. The current top on the SteelDev leaderboard is DeepSeek V22 at 74.3%, third-party verified.
That's a remarkable trajectory in about 2 years.
And then Web Voyager, which uses live websites and a GPT-4v judge, has self-reported scores from H Company's Surfer 2 at 97.1%. But the caveat from SteelDev is important here. A 70% on WebArena and a 70% on Web Voyager are not equivalent. Different tasks, different environments, different graders, different difficulty levels. You can't compare them directly.
OS World is the desktop automation one.
OS World gives you a full virtual computer environment, Ubuntu and Windows, with 369 tasks ranging from single app operations to multi-app workflows. Human baseline is 72%. GPT-4o's baseline was 17.8%. The current top is GPT 5.4 self-reporting, 75%, Claude Opus 4.6 at 72.7. Agent S3 from Similar AI is at 69.9% third-party verified and open source, which is notable.
There's also TAU-bench for customer service scenarios, which feels very relevant for anyone building support agents.
TAL, Bench from Sierra Research simulates multi-turn customer service with domain-specific API tools. The Hall verified top score on the airline domain is 56% with 04 mini-high at about $11 per run, which is Pareto optimal. Claude 3.7 Sonnet and Opus 4.1 both reach 52%, but at much higher cost. For anyone building a customer service agent, this is probably the benchmark to pay closest attention to because the task structure most closely matches what they're actually deploying.
Okay, I want to get into the evaluation approaches for people actually building agents, because the public benchmarks are useful for understanding where the field is, but they don't directly answer, is my agent getting better?
Right, and this is where the practical toolkit diverges significantly from the leaderboard world. Let's start with LLM as judge, because that's where most teams are actually operating. The evolution here has gone through roughly 4 generations. Traditional metrics like Rouge and Blue have poor correlation with quality for open-ended tasks. Single LLM as judge using GPT-4 to score outputs gets you Spearman correlation of about 0.7 to 0.9 with human preferences, which sounds good until you realize the failure modes.
Length bias being the big one.
Length bias, self-model bias. Judges tend to favor outputs from architecturally similar models, style bias, and adversarial vulnerability. You can craft a response that's essentially nonsense, but that exploits the evaluation prompt to get a high score. The multi-agent judge frameworks try to address this. Chattival uses multiple LLM agents with distinct personas debating response quality and improve correlation with human judgments by 10 to 16% over single agent prompting. Court Evil uses a courtroom structure, judge, prosecutor, defense attorney, where the judge revises the score after hearing both sides.
The agent as a judge result from ICML 2025 is the one that really jumped out at me.
This is from Juga et al., and the setup is using an agent to evaluate another agent's entire trajectory, not just the final output. They applied it to DevAI, which is 55 realistic AI development tasks. The agent judge's decisions differed from human majority vote only 0.3% of the time. A single LLM judge disagreed 31% of the time. The agent judge even exceeded individual human evaluators in consistency.
0.3 versus 31. That's the difference between trajectory evaluation and output. Only evaluation.
And it points to why output-only evaluation is often insufficient for agents. If your agent makes 10 tool calls and the final answer happens to be correct, output-only evaluation will rate that highly. But if step 4 used the wrong tool and step 7 hallucinated a result that happened to cancel out step 4's error, you have no idea your agent is doing something broken. Trajectory evaluation catches that.
LangChain's framework breaks this into 3 dimensions, right?
Grounding and context use, did the agent retrieve and reason over the right information, measured through faithfulness, context precision, and context recall. User experience quality, did the conversation achieve the user's goal, measured through topic relevancy and outcome success? And security and safety, did the agent stay within policy boundaries, checking for prompt injection and policy compliance? That third dimension is one that a lot of teams ignore until something goes wrong in production.
Let's talk about the custom harnesses, because this is where most teams are going to spend their actual evaluation budget.
BrainTrust and Langsmith are the 2 dominant platforms right now. BrainTrust's key differentiator is their Loop feature, an AI assistant that writes custom scores from natural language descriptions. You describe what you want to measure, it generates the scorer. They also have remote evals and playgrounds for no-code agent testing. The pricing is free tier for small teams, 5 users, 1 million spans per month, 10,000 scores, and then $249 a month for Pro.
The reported impact numbers they cite are striking. 30% accuracy improvements within weeks. One customer service app reducing escalations by 3,000 per day after systematic evaluation.
Those are self-reported, so take them with appropriate skepticism. But the underlying mechanism is real. When you're running production traffic through an evaluation framework and routing failures to domain experts for annotation, you're creating a feedback loop that genuinely accelerates improvement. The Langsmith approach is similar. Native LangChain and LangGraph integration, automatic tracing, annotation queues, online evaluations running judges on sampled production traffic.
The human evaluation piece is worth dwelling on for a moment because I think there's a temptation to think you can automate your way out of it entirely.
You can't. Human evaluation remains the gold standard. The GDP-Val project from OpenAI is the most ambitious recent effort. 1,320 tasks across 44 occupations created by domain experts with an average of 14 years of experience. Blind review by industry experts comparing model outputs to human professional outputs. The key finding, Claude Opus 4.1's outputs were rated equal or better than human professionals on just under half of tasks. Models complete tasks about 100 times faster and 100 times cheaper than human experts, though that doesn't account for oversight and iteration costs.
The 100 times faster and cheaper number is the one that'll get quoted in board meetings. The oversight and iteration cost caveat is the one that'll get ignored.
The practical human evaluation protocol for agent builders, annotation queues where complex traces get routed to domain experts, calibration sessions before annotation starts to align reviewers on scoring criteria, multi-annotator consensus using majority vote of 3 to 5 experts as ground truth, and blind review mixing model outputs with human outputs to prevent rater bias. And critically, the production to dataset loop. When monitoring identifies a failure in production, convert that trace into a test case with the corrected trajectory as ground truth. Your production failures are your best source of evaluation data.
So if I'm an agent builder trying to answer Daniel's core question, how do I know if version 2 is better than version 1? What's the actual workflow?
A few things. First, don't rely on a single public benchmark. AgentBench showed that cross-domain performance is highly variable. Pick 2 or 3 benchmarks that reflect your actual use case. If you're building a coding agent, SWE-bench Pro with standardized scaffolding is your primary signal. If you're building a web agent, WebArena with third-party verification. If you're building a general assistant, GAIA via AAAL.
And on the cost dimension, always include cost in your evaluation, not just accuracy.
Always. Hale's Pareto frontier approach is the right mental model. The question isn't which agent scores higher, it's which agent is on the Pareto frontier of accuracy and cost for my deployment constraints. Those are often different agents.
The scaffolding point matters here too. If you're comparing version 1 to version 2 of your own agent, you can hold the scaffold constant. But if you're comparing your agent to a competitor's published score, you often have no idea what scaffold they used.
Which is why third-party verified scores matter. SteelDev distinguishes between self-reported and third-party verified scores throughout their leaderboard, and the gap is consistently large. On GAIA, 18 points. On SWE-bench Pro, GPT 5.3 Codex CLI self-reports 57%, while the SEAL standardized score for GPT 5.2 Codex is 41%. 16 points of scaffold and reporting methodology.
There's also the question of what you're actually scoring. Binary pass-fail misses partial progress.
This is a real limitation of SWE-bench's approach. An agent that fixes 9 of 10 bugs in a task scores the same as one that fixes 0. You can't measure incremental improvement in the binary regime. SWE-bench Pro's 3-stage human augmentation helps. They add problem statement, requirements, and interface specification, but the fundamental binary nature remains. The emerging solution is process reward models and trajectory scoring, where you score the path, not just the outcome. That's where the agent as a judge work is heading.
What about ARC-AGI2 and some of the other benchmarks designed to be intentionally hard?
ARC-AGI2 from 2025 is worth mentioning because the scores are deliberately low. O3 at high compute gets about 4%, Gemini 2.5 Pro at about 2%. The point isn't to measure absolute capability, it's to maintain a benchmark that resists memorization and signals where genuine reasoning improvement is happening. Low scores on ARC-AGI2 aren't embarrassing, they're the point. It's a leading indicator, not a performance metric.
There's also BrowseComp from OpenAI for deep web research.
BrowseComp is interesting because it's explicitly designed so most agents fail. Multi-hop web research requiring synthesizing information across many pages. Kimi K2. Thinking from Moonshot AI is at 60.2%. OpenAI Deep Research at 51.5%, and then a dramatic drop-off. WebSailor 7.2b at 12%, GPT-4o with browsing at 1.9%. The distribution tells you this is measuring something qualitatively different from standard web browsing tasks.
Okay, practical takeaways. If someone is building agents today and wants to set up a serious evaluation practice, what's the actual guidance?
Start with the benchmark selection question. Be honest about what domain you're in. SWE-bench Pro for code agents, GAIA via HAL for general assistants, WebArena for web agents, TAU-bench for customer service. Use HAL verified scores, not self-reported scores. Always track cost alongside accuracy.
For your own internal evals, the production to dataset loop is probably the highest leverage thing most teams aren't doing.
Every production failure is a test case waiting to happen. When your agent fails in the wild, capture that trace, have a domain expert annotate the corrected trajectory, and add it to your eval suite. That's how you build evaluation coverage that's actually calibrated to your real failure modes, rather than the failure modes that benchmark authors happen to anticipate.
And the scaffolding discipline matters enormously. If you're running AA/B tests between agent versions, hold the scaffold constant. If you change the model and the scaffold at the same time, you have no idea which change drove the improvement.
The Scale AI Failure Mode Analysis on SWE-bench Pro is instructive here. For the strongest models, context overflow is the dominant failure, 35.6% of Sonnet 4 failures. For smaller models, tool use inefficiency dominates at 42%. Semantic understanding failures account for 35.9% of Opus 4.1 failures. Knowing which failure mode is your bottleneck tells you where to invest. Better context management, better tool selection logic, or better reasoning.
And don't sleep on the latency dimension, even though the benchmarks mostly ignore it.
Completion tokens as a proxy is imperfect, but better than nothing. Hail tracks this. If you're deploying an agent where a user is waiting for a response, a 45-minute completion time that scores slightly higher on accuracy is almost certainly the wrong trade-off.
The field is in a genuinely interesting place right now. The benchmarks are getting more rigorous. The move from Verify to Pro on SWE-bench is a good example. But the gap between benchmark performance and what you'd actually want to deploy is still significant.
The CUB benchmark, which tests 106 end-to-end workflows across 7 industries, has a top score of 10.4%. 10%. For end-to-end real-world workflows, even the best agents are failing 90% of the time. That's not a reason to panic. It's a reason to be precise about what you're deploying and what your fallback mechanisms are.
All right. Big thanks as always to our producer Hilbert Flumingtop. And a genuine thank you to Modal for providing the GPU credits that keep this whole operation running. This has been My Weird Prompts. If you want to find us, search for My Weird Prompts on Telegram, and you'll get notified when new episodes drop. We'll see you next time.
See you then.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from slow